Okay, good afternoon, everyone. My name is Ke Chen. I'm a PhD candidate from the Hong Kong University of Science and Technology. My supervisor is Professor Jack Cheng. And it's my great honor to present my research to you. This is the title of my research. It's, basically, I developed a BIM-based location-aware AR collaborative framework for facility maintenance management. Although I put augmented reality in my title, but somehow I was kicked out of the AR session. But I hope this one is not too boring to you. So first of all, I'm going to give some background information. Nowadays, FM, facility management, is a very hot topic. And among all the FM activities, facility maintenance management, FMM, which refer to activities taken to prevent functional failure, accounts for more than 65% of the total FM cost. So that's why I want to focus my research on FMM. So here's a very typical workflow for FMM. So at the beginning, maybe an inspector or a site user spots some problem on site, and he may report this problem to FM office, and the person in charge, or the FM manager, may make the decision and instruct corresponding people, maybe a technician, to go to site and check and repair. So this is the workflow, but currently still a lot of work are paper-based. So this kind of activities are very low efficient. And another problem is, as you know, some facilities are normally hidden from users, like the ventilation ducts or the water pipe. They may be above the ceiling panel. So when you want to inspect those facilities, you may need a ladder and climb and remove the ceiling panel until you can really visualize them. So this kind of traditional measures are very low efficient. So that's why innovation is needed to enable users to directly visualize and interact with their surrounding facilities. So in my research, I propose to use augmented reality, which can combine the virtual world with the real world. As you can see in this video, so the user with some MR or AR, some AR device, he can actually visualize some virtual information or virtual model in their surrounding environment, and those virtual information are actually can be updated, can be interacted. So with this kind of technology, the users can visualize and interact with the surrounding facilities. So before implementing this one in FMM, I actually did a literature review and found many related papers. And from those papers, I actually found two major research gaps. The first one is about spatial resolution, and the second one is about collaboration. So first, because I'm doing the facility maintenance management mainly for building component, so I prefer to use markerless AR. You may heard of this one, marker-based and markerless. For marker-based, we need to attach some marker, and we scan the marker, we can see some information. But we just don't want to attach marker everywhere because it's very like tedious work or it's not beautiful enough in the building. So we just want some markerless approach. And nowadays, the GPS is the most widely used method for markerless AR. But because we are doing something for building component, and most of the time it actually taking an indoor environment. But as you know, the GPS, the performance in indoor environment is very bad due to the signal block by the building component. So we don't want to use GPS. But there are also some other technology like the RFID or UWB, which can provide better accuracy in indoor environment, but this kind of technology, they require extra device. You may need to set up the beacon, or you need routers, or you need some other device to receive the signal. But for FMM, I just want the users to directly use their own smartphone, because everyone has smartphone. I just want them to use their own device to do the work, so they don't need to carry a large device to do that. So that's why a more accurate localization method that can be applied to our normal mobile device is needed in an indoor environment. And the second research gap is about collaboration. So as you know, the project in the OIM or in FMM consists of complicated work, and sometimes they require multiple people from different places to collaborate with each other, just like showing this typical workflow. There's a site inspector and also the FM manager in the office, and also the technician, they maybe also work on site. So they require people from different locations to collaborate with each other. But currently only limited trials of AR collaboration have been implemented, and most of them are actually face-to-face interaction. So basically, they stay in the same room, and with some shared coordinate, they can collaborate with each other. But for us, to further improve the efficiency of collaboration, we want to implement the remote collaboration. So this is the objective of my research. The objective is to develop a location-aware AR collaborative framework for FMM. In my research, I use Wi-Fi fingerprinting for localization, and I use BIM building information modeling as my data source, and I use a collaborative AR as a user interface for people to visualize and read the surrounding information. So this is the framework of my research. It mainly contains 3 parts. The first one is about localization. As I mentioned, I use Wi-Fi fingerprinting and also incorporate some algorithms like k-means clustering or propose a localization algorithm and also some room detection algorithm. And there's a shared database which I use BIM as my data source, and I use some different BIM-related APIs to extract information from BIM models. And the third part is about the user interface, the collaborative AR. So first, I'm going to talk about the localization part. I'm using Wi-Fi fingerprinting. I didn't know the propagation of different Wi-Fi signals from different Wi-Fi routers can form unique fingerprints at different places. So that's the idea of this technology. And in my part, I basically consider the following 4 different types of information. The first one is the fingerprint ID, and then the map basically refers to the location, where is it, location, and also the most importantly, the measurements. So for measurements, we consider the BSSID, which is just the MAC address of each router, and also the RSSI, the received signal strength of each router. And here's an example of a fingerprint. So we have the ID, location, and also the measurements. So currently, a commonly used algorithm for this kind of localization is the 1NN algorithm. It is a special case of KNN. So in this case, K equal 1. And here, with this equation, we can actually find the nearest fingerprint. And once we get the nearest fingerprint, we can use that fingerprint to represent your current location. So for example, I store a lot of fingerprints in our library, in the library of my university. This is all the stored fingerprints. And if I'm standing I'm standing here, and the algorithm can know that, okay, 107 is the nearest fingerprint, and then the algorithm will use the coordinate value of 107 to represent my current location. That's how this 1NN algorithm works. But as you can see, there's some problem in this algorithm because it uses a particular fingerprint to represent my current location. But what if I'm standing outside this bounding box, or if I'm standing between fingerprints, but it cannot use a particular, the real coordinate value to represent. It still use the nearby fingerprint. So there's already error in this algorithm. So that's why I propose our algorithm. I call it the softmax-based weighted k nearest neighbor, SWKN algorithm. I propose this one, which can consider multiple fingerprints as my reference points to calculate the real location. So in this one, for example, if I'm using 4 nearest fingerprints, I'm standing in the middle, and we use all of the 4 surrounding fingerprints as reference points to calculate my real location, so which can provide a better localization accuracy. And in this one, I also consider the different signal strengths from different fingerprints, because the fingerprints with higher received signal strengths are more reliable because they suffer less from the fluctuation or attenuation. So the more RSSI value, the more reliable they are. And I use the softmax function, which is just a function for probability distribution to calculate the location. This is the proposed equation. And with this algorithm, I can get the real location of the user. So after propose this one, I actually compare this proposed algorithm with the traditionally used 1NN algorithm. And here is, I just did an experiment in my library, and this is the conditions are set, and here's the result. I found that for the previously used 1NN algorithm, the localization accuracy was about 91 centimeter, and with the newly proposed algorithm, the SWKN, the accuracy can reach 52 centimeter, so you can say there's a 43% improvement, and also the standard deviation, as you can see, the standard SDA is also decreased a lot. So the stability of this algorithm is also better than the previous algorithm. So we can claim that the localization accuracy and the stability of the proposed SWKN has been improved compared with the traditional one. And after getting the real location information, I also propose a room detection method because I just want to always display the corresponding facilities. Only the facility may be in a limited area or in the corresponding room rather than the whole floor or the whole building to reduce the computation workload. So with this one, I think some of you may be very familiar with the recasting algorithm. So it just basically, if I'm standing here, like I'm standing in point P1, and if I want to know whether I'm inside this room or not, I just set another point and link these 2 points. If this line, the total number of the intersection points with this line and the bounding box is odd, it means this P1 is inside the room. Otherwise, it's outside the room. So for example, here for P2, the total number of intersection points is 4, so it's outside the room. So basically, with this one, I can know which room I'm currently in. And the next part about the shared database, I use a concept of a relational database, and I store this following information, including some dimensions and the coordinates and some semantic information, room information, etc. And also use, because it's still based on BIM, so I use the APIs from different BIM software to extract the information, including the facility information from BIM models, so I can directly get all the semantic information or geometric information on each facility from BIM models, and I also need the room information because for the room detection algorithm, I need to know the bounding area of each room. So I also need the coordinates of each room. So I also use API to extract the room information. And about the user interface, I need to first of all I need to know where to display the virtual facility. So first of all, because I already have the real-time location information, so basically I just set the coordinate value of my current location to the view camera. So whenever I'm using an AR device, for example, I'm standing under a sprinkler, I just use an AR device, I look above, and I can see the sprinkler will be exactly above my head. But this one is only for location. But as you know, for only location, so although it's fine for a sprinkler, but if there's a pipe above my head, but with only the location information, but the pipe may be in this direction or in this direction. We cannot decide the direction of the pipe. So we also need to use some other functions. Like in my case, I use the compass and also the gyroscope to decide the location. So basically, with this workflow, I can set the correct direction of each facility. So this is for the alignment. And for information visualization, I use a lot of information panel to display all corresponding information, and we can add some interaction box to update the information, and also use the PHP files with SQL query commands to link my AR application to the online database, so that multiple users can directly read and update the information from the database. And also, because I'm doing a remote collaboration, I want the people from remote location to have a direct understanding of the site situation. So I just incorporate the screen sharing function. I use the TCP protocol, and on the server socket, I just capture each frame of the screen and compress each frame as a JPEG image, and I send this image streaming through the network to a client socket, and on the client, I just decompress and display corresponding video. So that's how I did it. I just like showing this in this photo. This is AR app on our computer, and on our remote computer, we can see what's going on in real time. So here, and then I just test this one in our university. This is the real environment I set. So with all the required software, and this is what programming language I use, and also what device, the hardware I need. And this is just a short video to show the functionality of the system. So the user interface is actually very simple. I just want to show how it works. So this is the screen of the phone, and the user is working outside, and once the device detects the current location, it can display corresponding facilities. These are all the MEP facilities above the ceiling panel. And once the user wants to visualize or inspect any facility, just by a simple click on the facility, and the corresponding information will be displayed, and he can also update the information. And on a remote computer, another user can visualize what's going on site in real time, and he can also visualize all the corresponding information. And there's a screen to show the real situation on site. So basically, this is how this framework works with two different devices. And also did some user tests to evaluate this framework. So basically, I invite a lot of students from our department to perform some particular tasks with the proposed AR framework, the AR system I developed, and also with a traditional paper-based method. So I just compare the results of these two methods. And here's the result. So first of all, about the time of completion, as you can see, with the during inspection with the AR method, the time of completion is around 31 seconds, and with the traditional 2D-based method, it's around 90 seconds. And in repair also, the time of completion of the AR method is much better than the traditional 2D-based one. And also the P values refer to the analysis of variance are less than 0.05, so it can be concluded that the developed AR system has a significant advantage in reducing the completion time. And also separate the time into operation and the communication. So as you can see, for operation, actually the two methods are not much, there's not much difference between these two methods. The major difference is from the communication. So the major contribution is for communication, the efficiency of communication between people from different locations. So compared with the traditional method, the time of communication for the AR method can be reduced by this amount, indicating a great improvement in terms of the collaboration or communication. And also about the localization, for the proposed AR system, actually the localization error was around 52 centimeter, and for the traditional method, it's around 135 centimeter, and the stability is also better. And this is the correct ratio to the ratio whether the participants can find the correct facility or not. So it also shows an improvement. And here comes to my conclusion. So to improve the efficiency of FMM, we develop a BIM-based location-aware collaborative framework. And we use Wi-Fi fingerprinting for localization. We use BIM as my data source. And also we use AI to provide a better user face for people to directly visualize and update the information. And we propose a SWK algorithm, which has been proved to have better accuracy and stability compared with the traditional used one algorithm. And this one is used for Wi-Fi fingerprinting. And also the users in remote location can visualize the site situation and interact with the site facilities in real time. And also, as shown in the results of the conducted experiment, the AR collaborative system has an advantage in improving the collaboration efficiency and locating the correct facility. So there are still some limitations in this framework because I'm using Wi-Fi fingerprinting. So the whole area, of course, should be covered with Wi-Fi signals. It's hard to implement this one in an indoor environment or environment without the Wi-Fi routers. And also the varying Wi-Fi signals can influence getting the nearest fingerprint, thus reduce the localization accuracy. So for my future work, I will just focus on improving the localization accuracy and also reducing the dependency on the environment. Yeah, so that's all for this presentation. I hope you all enjoy this one. Thank you.